Incorrect column ordering in a composite index frequently transforms a sub-millisecond lookup into a performance-killing table scan that consumes massive server resources. A composite index functions by concatenating values from multiple columns into a single sorted search key within a balanced tree structure in the database storage engine. The database engine navigates this structure from left to right, meaning the specific order of columns dictates the efficiency and the depth of the tree traversal. The equality sort range rule provides a definitive template for ordering index columns to ensure maximum query performance in high-volume structured database environments. Equality predicates are the most powerful filtering tools because they allow the search engine to pinpoint exact branches in the tree without scanning extra data. When the database engine encounters an equality filter, it can safely ignore all other branches and focus its search entirely on the relevant subtree containing matches. This search precision is maintained as long as subsequent columns in the query also use equality filters, allowing for deeper and more specific index navigation. Range predicates, including operators like greater than or less than, represent a significant transition point where the index search process changes from seeking to scanning. A range filter allows the engine to find a starting point, but then requires it to scan all subsequent leaf nodes sequentially until the stop condition. Crucially, once a range filter is applied, the sorted order of any following columns in the index becomes useless for further logarithmic tree navigation and filtering. This is why range columns must be placed after all equality columns to prevent the premature termination of efficient point-based lookups during the search phase.
Sorting operations are another critical factor in index design, as the database can avoid expensive in-memory sorting if the index is already pre-sorted. The database can read index entries in their natural order and stream them directly to the application if the index follows the query sort order exactly. For an index to satisfy a sort requirement, all columns preceding the sort column must be filtered using equality predicates in the structured query language statement. If a range filter precedes a sort column, the database is forced to perform a manual sort operation after retrieving the range results from the disk. The equality sort range rule dictates that equality filters come first, then sort columns, and finally range filters occupy the last position in the index. Selectivity is often misunderstood by developers who incorrectly believe the most unique column should always be placed at the very front of every composite index. In reality, a low-cardinality column used for an equality filter is frequently more beneficial than a high-cardinality column used for a range search operation. An equality filter on a column with only two distinct values still allows the database engine to eliminate half of the entire index search space immediately. In contrast, a range filter on a unique identifier might still require scanning 90% of the index if the query range is sufficiently broad or unselective. Index skip scans are an advanced optimization where the engine jumps between values of a leading column to reach a middle column required by the query. Skip scans are only effective when the leading column has a very small number of distinct values, and the query happens to skip that leading column entirely.
Relying on skip scans is risky because as the data volume and cardinality grow, the overhead of jumping between branches becomes prohibitive for the database engine. Covering indexes are a powerful strategy where the index contains every single column requested in the select list of the structured query language statement being executed. By using a covering index, the database engine never needs to access the actual table pages, which significantly reduces expensive and slow random disk access patterns. Include columns are non-key values stored only at the leaf level of the index, providing covering benefits without increasing the complexity of the tree structure. The width of the index key directly impacts the depth of the balanced tree and the number of pages residing in the database buffer pool memory. Wider indexes lead to fewer entries per memory page, which increases the number of logical input-output operations required for every query executed by the system. System analysts should use the explain plan command to identify whether the database is performing an efficient index seek or a less optimal index scan. An index seek indicates that the engine is traversing the tree hierarchy, while an index scan suggests a horizontal traversal of millions of individual leaf nodes. Access predicates shown in the query plan indicate columns used to narrow the search range within the tree structure itself during the initial traversal phase. Filter predicates represent conditions that are checked only after the index data is retrieved, which is a much less efficient filtering mechanism for large datasets. A well-ordered index maximizes access predicates, while a poorly ordered one relies heavily on filter predicates to discard irrelevant records after they are already read. Consider a table for user accounts where queries filter by the active status and a registration date range while sorting by the username alphabetically. The optimal index for this query pattern would place the status column first, followed by the username column, and finally the registration date column at the end. Placing the registration date before the username would force the database to sort the results manually because the range scan on date breaks the natural index order. The in operator can often be optimized by modern engines as a multi-point lookup, which behaves more like an equality check than a standard range scan. However, many database engines treat the in operator as a range if the number of provided values exceeds a certain internal threshold or limit during execution. Inequality filters like the not equals operator should always be placed at the very end of the index because they never allow for efficient point lookups. Modern query optimizers utilize complex multi-column statistics to accurately estimate the cost of various potential index access paths and the specific column order. Consistently maintaining these statistics is an essential task for large tables because outdated information can lead the optimizer to incorrectly ignore a perfectly ordered index. Write performance is the primary trade-off for composite indexes, as every update to an indexed column requires a corresponding update to the balanced tree structure. Columns that change frequently should be placed at the end of the index or omitted entirely to minimize the cost of maintaining the leaf node sequence. Regularly auditing index usage via system views allows analysts to identify redundant or unused composite indexes that consume storage and slow down data write operations.
The goal of index optimization is to provide the shortest possible path to data, and the equality sort range rule remains the most reliable method. Multi-column indexes also play a vital role in optimizing join operations, where the order of join keys can dictate the choice of join algorithm by the optimizer. In a nested loop join, the inner table should have an index where the join columns are in the leading positions to facilitate fast repeated lookups. Parallel query execution can also be impacted by index design, as certain scan patterns are easier for the engine to distribute across multiple processors simultaneously. Database fragmentation can reduce the performance of the range scan portion of the index search by increasing the physical distance between stored leaf nodes on disk. Implementing the equality sort range rule ensures that every query performs as few logical reads as possible, preserving system resources for high concurrency production workloads.